Uh, ah, okay. Okay. Is it better now? Yeah? Okay, yeah, I hear myself, right? Do you hear me? Cool.
Okay, we're going to start the session on attacks on post-quantum crypto. So there are two talks today. The first one is, does the dual shift attack on learning with error even work? By Leo Duca and Ludo Puls, and Ludo is going to give the talk.
Okay, thanks for the introduction. So the security of a lot of lattice-based schemes, like for example, Kyber and the lithium, these depend on the security, on the hardness of the so-called bounded distance coding problem. What this problem is you're given a lattice and some target that's a lattice point with a small error added to it. The problem is of recovering this original lattice point from it. So what kind of attacks do we have against this problem? They fall into two categories. So on one side, we have the primal attack. Here you embed the lattice and the target into another lattice, and on this lattice you solve the shortest vector problem. And on the other hand, we have the dual attack. And here we first build a function that can distinguish if a target was from this BDD distribution, or it's just a target that is uniform modulo the lattice. And then we make some guesses and we determine which guess was the correct one. That finds a part of the secret. And this primal attack is well studied, well understood, theoretically, experimentally. However, this dual attack has received much less experimental attention so far. So a bit of history about the dual attack. It started with Aronov and Regev, published a paper that you can use dual vectors to do this distinguishing trick. And we've seen a lot of recent developments in the dual attack. So first, there was the idea that you can use a lattice shift to generate a lot of dual vectors that are short. And then 2 years ago, Johansen realized you can speed up this evaluating of the distinguisher by using a fast Fourier transform algorithm. And then last year, Matsov published a report where they improved this dual attack even further with some modulus switching technique. And here they claim that this dual attack outperforms the primal attack. So it's an interesting case to study. And all these recent improvements so far have been specific to the LWE problem, learning with errors. And this is bounded distance decoding for a particular class of lattices. So what we do in our paper is we generalize this FFT trick by Johansen to the general case of BDD for any lattice. And it gives a lot of geometric insight in how this dual attack works in this case. And we even show a small improvement we can make to the attack. However, our second contribution is that is a heuristic used in all these recent works. And we show that these lead to two contradictions. And what this shows is that this distinguisher function does not work as well as it was predicted under the heuristic. And we also did some experiments on this. And these also show some deviation from the prediction in practice on small instances. But overall, then we conclude that this cryptanalysis that is derived from the heuristic it ultimately overestimates the success probability of the attacks, also in the big attacks against crypto schemes. So let me start off with just explaining what the dual attack is by giving our general framework to this dual attack. So the problem we want to search is alpha BDD. It's a search problem. You get the lattice, the target, and the target is a lattice point that's taken randomly somewhere from the lattice, and the error is added with a norm that is concentrated around alpha times the shortest vector of the lattice. And the problem is recovering this original lattice point. So alpha is a parameter that determines the difficulty of this problem. As alpha is small, there's not that much noise. So this problem is very easy to solve. And if you have alpha below 1/2, there can only be at most one lattice point that is close enough to this target. And even when alpha is in between 1/2 and 1, on average, in a random lattice, we expect only one lattice point to be close enough to this target. However, when you move alpha above 1, suddenly you have infinitely or exponentially many lattice points that can be close enough to this target, and that makes this problem very hard to solve. So the best you can do is make a list of all the lattice points close enough to the target and then pick one of them randomly. So the probability of guessing right becomes very small in this case. And we want to solve this BDD problem by using the dual lattice. What's the dual lattice? It contains all the points that have an integer inner product with all of the primal lattice points. And how you can think about the dual vector is some kind of wave function that's periodic with a lattice. By taking this inner product with a dual vector and take it modulo 1, gives this rainbow pattern. So this rainbow pattern also can be used as a score function. So for example, if a target is from the lattice, this cosine is equal to 1, and that's the maximal value. And what is nice is that even when target is still close to the lattice and this dual vector is somewhat short, then still this score is going to be very large. And when you have a target that is just uniform from the torus, so space modulo the lattice, on average it's going to be 0. However, there's still somewhat an overlap between these two distributions. So we want to improve this distinguisher to separate the two distributions. That's where people use this lattice sieve. So the lattice sieve generates exponential number of short dual vectors. And now we combine these score function into one score function given by the different dual vectors, and we sum them. However, this score function is more difficult to analyze. So what people have been using is this independence heuristic. What it says is that this set of dual vectors gives scores that are mutually independent. And that way, they could analyze this score function as follows. So then it separates, and from this analysis, they see that a uniform target gives a score function roughly 0 on average with a high probability. And if a target is from a BDD distribution, with a high probability, its score is going to be large. So what we then can do is take a threshold value, and everything that's every target that has a score above it, we consider a BDD target, and everything that's below it, we consider a uniform target. And then with a high probability, we're right all the time. And this is a way to solve the decision BDD problem, so distinguishing between the two. But we wanted to solve the search problem. So to use this decision BDD thing, we take a sparsified sublattice, and then we use this distinguisher on this sparsified sublattice. And how you can use this is then making a guess of where this original lattice point is, in which of the cosets of this sublattice. And if you make the right guess, then the difference of the target minus the guess is a BDD target in the sublattice. So that then becomes our general dual attack. So first we take some sublattice of our choosing, and then we run a lattice sieve on the dual of the sublattice to have this distinguish function. And then we can write this lattice as a union of all these lattice cosets. And we just make the guess that the guess that maximizes this score contains this original lattice point from the target. And if we're right, we just recover the part of the secret. And we can actually repeat this dual attack multiple times. And every time the BDD instance becomes easier over time, and then you can recover the whole secret. And this is where this FFT trick comes in. So if you evaluate the score function naively, the time is linear in the number of dual vectors. and the number of dual vectors was exponential. So this FFT allows it to speed up this evaluation for many targets, and then the time drops to almost constant time per guess, so logarithmic in the number of points you want to evaluate it at. And what we show, so with this general dual attack that gives some geometric insight, is that you can actually run this FFT trick on any sparsification you want. It has much more flexibility, and it also shows that you can run this dual attack for any lattice you want, so not necessarily the lattices used in the LWE case. And yeah, with this flexibility of the sparsification, we show that we can improve this attack a little bit, and that's in the paper. However, yeah, what's more important for now is that we show that this independence heuristic that is used in the score function, it leads to two contradictions. So I'll start with the first one. The first one is about the decision BDD problem. So there was a paper analyzing decision BDD, and it says that if you want to solve alpha BDD distinguishing from uniform, then you can take a beta according to this formula, and then taking the shortest beta to the n dual vectors allows you to distinguish between uniform and alpha BDD with a high probability. So if you check this formula, it also says that even for alpha above 1, this should be possible based on this independence heuristic. So yeah, earlier on I said search BDD was statistically impossible for alpha above 1. So maybe you're hoping now that decision BDD is somewhat different than this search BDD, and it could still be possible to do. However, there's a theorem that says that errors that are sampled uniformly from a ball of a radius alpha lambda 1, so these form BDD targets, these become statistically indistinguishable from uniform errors when this alpha is above 1 as the dimension increases. And because you can't distinguish between them statistically, this means that there cannot be any adversary, no matter what the runtime is, that can distinguish with a higher probability, much higher than 1/2. So that's the first contradiction we get. And the second one is more closely related to what we do in the dual attack, and that's this problem of having one alpha BDD target among many uniform targets. And the task is to find which one was sampled from the alpha BDD distribution. And this is what is done in the dual sieve attack. So we have a lot of guesses, and one of them was a BDD target, and that was the right guess. And all the others were kind of uniform targets. So the dual sieve attack tries to solve this problem. And yeah, it is important to know then what the number of targets is T that we can use to still have a high success probability in distinguishing the BDD target from it. So what's the chance of success? Well, if there is a failure in this, that means that either there was a BDD target that had a low score, so a score below the threshold, or one of these uniform targets has a score that is above the threshold. So this last one is much more likely. And if you do the math with the independence heuristic, you can use a tail bound of either a Gaussian or you use a Hoeffding inequality, and you get a probability that is exponentially small in this quantity here. And when this alpha is not too large, even this quantity increases exponential with dimension. So if you combine them together, this means that under the independence heuristic, the claim is that it will work, the attack, for a number of targets that is double exponential in the dimension. And that's an awful lot of target points. So can this be true? In fact, cannot be. So for this, consider this lemma, and this considers the probability that you have a uniform target modulo the lattice, and this gives the probability that it's close to the lattice with a distance as most r lambda 1, and the probability that it's at most this distance away from the lattice, it's r to the n. That's a single exponential number. So if you take a number of targets that is alpha to the minus n and take it much larger than this, like somewhat larger, then there's going to be one of these uniform targets that is closer to the lattice than the alpha BDD target. And what this means is that because it's closer, this target has a higher score. It's very likely that this target has a higher score than alpha BDD target. To say it's like at least 50% chance that it has a higher score. And that means this attack doesn't work with a high success probability anymore. So yeah, what's going on? How do we get these contradictions? And that's basically kind of the only heuristic I showed here at this point. This independence heuristic that says that these scores are all independent. That was what the heuristic said. But as we see, this cannot be the case. So it's kind of important that targets are close to the lattice. That is not considered by this heuristic. So these contradictions are in particular regimes, and we wanted to test also if these contradictions somewhat are also visible for small experiments. So we took a number of uniform targets in small dimensional lattices, or 60, 80, depending on what small is. And with a lot of random uniform targets, we saw that this score, although it initially follows this waterfall, so in the log plot, the probability decays as a parabola, like a Gaussian would do. At some point, it seems to hit the floor and then decay much slower than expected based on this independence heuristic. And what this means is, so the success probability of the attack is much smaller in practice than predicted under the independence heuristic. And why? That's because this score is going to be large with a larger probability than predicted for a uniform target. So there's a higher chance that it's going to pick the wrong one in the attack. And what's interesting is that this phenomena is also appearing in coding theory. I think that's the next presentation. So there they also had some decoding failure rates where the probability decayed like a Gaussian, but then hit the floor and then was decaying slower. And just to add, so we also analyzed the BDD distribution. And here we saw that the prediction is quite far away from the experimental values. So in particular, the variance of the score was much higher, but also the median, so the point where the probability is a half of having a score below some value. This was also smaller than predicted. And what this means is that the score for the right guess is much more likely to be smaller than what was predicted. So yeah, it's a double effect. So even with the BDD distribution, we see that this independence heuristic overestimates the success probability of the attack. So yeah, there seems to be some things wrong, missing in analysis. What can we do? So ultimately, so this analysis seems to be somewhat off. And this success probability of the attacks that are given are significantly overestimated at this point. The chance of giving the right guess of the secret is much lower. This means that we currently do not have a precise knowledge of how hard this BDD is with respect to this dual sieve attack. So that's something to improve. But yeah, so just a sneak peek of what we've been looking into now currently. So we're trying to describe the score distribution more accurately of the BDD with the theory of Bessel functions. It gives quite an accurate prediction based on a different heuristic. And we also predict this floor phenomena for uniform targets. And I guess this work shows that when you use a heuristic in a cryptographic attack, it's supported to stress test this heuristic on small dimensions and put it to the extreme and check if it holds. So that's also when we take want to use a different heuristic, we really need to stress test this if it makes sense. And with that, I would, thank you for your attention, and I'm happy to take any questions.
So we have time for questions. Please come to the mic for asking questions.
I know you listed it on ongoing research, but I was just curious if you can say anything about how you have your new curve that's hitting that waterfall region, like how you generated that.
Yeah, so to get a prediction for this floor phenomena, we kind of used the contradiction we derived. So the contradiction was that even uniform targets can be close to the lattice. So if you somehow account for this effect, then you can predict this floor phenomena. Yeah.
Any other question? Okay. Let's thank the speaker again then. So the second talk will be presented remotely. The talk is about exploring decryption failures of BIKE, a new class of weak keys and key recoverings attack by Tianren Wang, Onion Wang, and Xiaoyuan Wang. And Tancrède will give the talk.
Okay. Good morning, everyone. My name is Tianrui Wang from Tsinghua University of Beijing, China. My co-authors are Anyu Wang and Professor Xiaoyun Wang from Tsinghua University. Today, I'm going to introduce our work, exploring decryption failures of BIKE, new class of weak keys and key recovery attacks. My presentation consists of 4 parts. First of all, I will cover the background of PQC, QCM-DPC, and BIKE. Next, I will introduce the guiding property we found and explain its impact on BIKE's decryption failure rate. Then I will provide a detailed overview of decryption failure attack based on guiding property for QCM-DPC. Lastly, I will conclude and discuss future work. It is widely recognized that a quantum computer could efficiently solve the integer factorization problem and the discrete logarithm problem using Shor's algorithm in polynomial time. Consequently, current public key algorithms such as RSA could become vulnerable to this quantum threat. To address this concern, NIST held a competition in 2016, inviting submissions for post-quantum algorithms capable of withstanding quantum attacks. Various approaches for public key algorithms have been proposed. In our context, we only consider code-based algorithms. Numerous algorithms were submitted to the NIST competition, with several advancing to the 4th round. Firstly, The Michaelis algorithm, invented in 1978, remains secure under many attacks over these years. However, the large public key sets and slow encryption speed are heavy burden in application. The rank code schemes are not performing well under algebraic attack, so NIST didn't select them to advance on in the PQC standardization process. As for LED crypt, a set of weak keys was identified in 2020 where a modified ISD algorithm results in an improved key recovery attack. By the way, a similar modified ISD for BAC is proposed in our paper. Finally, BAC based on MDPC remains a competitive candidate for its small key set and fast speed. Here, let's analyze QC-MDPC in details. Moderate density parity check, invented in 2013, can be viewed as a modification of Michaelis with higher weight. To simplify decoding, they add quasi-cyclic structure instead of GOPA code in Michaelis. Here is a version of algorithm offering true symplectic attack security. Initially, R is a ring with polynomials of degree less than R. An element y in R could be represented in two ways, as a polynomial y equals yo plus y1x plus so on, and as a vector y equals a tuple yo y1 until yr minus 1. Private keys ho and h1 are two vectors, each having half the weight of w. Public key h equals h1 multiplied the inverse of ho. During encryption, the message is represented as EO-E1 with 0 weights adding up to t. Cipher type is computed as EO plus E1H. During the decryption, the decoder processes SHO, HO, and H1. It transforms the polynomial multiplication into quasi-cyclic matrix big HO, big H1 multiplied by vector EO and E1. The decoder is called bit flipping algorithm. Given a matrix H and target vector S, the purpose is to find the vector E such that HE equals S. Another requirement is the weight of E is T. In the QC-MDPC application, parameter W and T are about O square root of N, much lower than GV bound, making the solution unique. The original bit flipping procedure operates as follows. Positions are flipped if such an action results in more satisfied parity checks. After each position is processed, the outcome of HE is updated. This iteration continues until reaching the maximum specified iteration count. Whether position is flipped is related to the UPC number. In the right picture, each variable node corresponds to a position of vector E. They are connected to several check nodes of vector S. The UPC number represents the count of unsatisfied check nodes, and the vector E is initialized as a 0 vector. Well, this algorithm is relatively straightforward and effective. It doesn't guarantee success on every occasion, resulting in a high decryption failure rate. Therefore, BAC chooses a modified version of bit flipping called black-gray flip. It uses fine-grained thresholds and makes smart, careful decision by checking before flipping. Initially, BAC's parameter only guarantee a DFR about 2 to the power of minus 30. The accurate DFR of bit flipping is hard to predict. In this figure, as the code length increases, logarithm of DFR falls quickly in waterfall region and slowly in arrow flow region. However, estimating DFR is important due to its potential vulnerability to attacks. In 2016, Guo established a relationship between DFR and the distance spectrum of secret key. The distance spectrum is the set of distances between any two ones in the secret key. As a result, when an attacker observes a decryption failure, he could predict the distance spectrum of secret key. Enough leaked information could help the recovery. However, such attack needs a lot of decryption failure to construct the distance spectrum model. So BAC chooses BGF with lower DFR for protection. Next, let's see the final application in BAC. The table presents 3 sets of recommended parameters by BAC, offering distinct levels of bit security. In our work, we only analyze the 128 level security, and those in other levels have similar phenomena. Facing potential decryption failure attack, BAC should guarantee the DFR lower than 2 to the power of minus 128. Additionally, it employs the Fujisaki-Okamoto transform to achieve chosen ciphertext attack CC security. Here is the key encapsulation mechanism of BAC. It uses some hash functions to protect the inputs. For example, in the encaps H, it computes EOE1 as HM. In summary, let's quickly go over the main points of BAC. Although some researchers provide theoretical DFR of bit flipping, as far as we know, there is no major theory about DFR of BGF. So BAC uses linear fit with experiments on small parameters to get the recommended ones. However, the accuracy of this linear fit remains uncertain in the presence of an error floor region. Another approach to estimate the DFR of BAC is using weak case. Sindre has found a set of weak case with high DFR. However, Wes's classification of this weak case doesn't undermine the indistinguished CC security of BAC. The way using weak case to establish the lower bound of DFR is as follows. Let's represent the key set as K. For any subset W of K, the average DFR is larger than the product of DFR W and the fraction of the size of W and K. The DFR W is the DFR in the subset W. There's still some remaining questions. Are these classes of weak case exhaustive? The identification of more weak case could potentially yield a higher lower bound of DFR. Then I will introduce the guiding property we proposed and how it affects the DFR of QCM-DPC. For this equation, we use the matrix form, turning polynomial multiplication into matrix multiplying vector. We call the ones of a vector getting in the first m positions as guiding property. In the left figure, the deeper the color is, the more ones gather in that area. If EO and HO has guiding property, the density of parity checks is described like this. Parity checks are more likely to be unsatisfied if more ones meeting together. Obviously, the deep blue area creates more unsatisfied checks. Consequently, the local UPC number becomes higher than normal. In the right table and iteration 0 with value 31 versus 26, the local UPC number in the first m positions is much higher than the global one. High local UPC number can lead to mistakenly flipped and eventually the failure of whole algorithm. Following the principal explanation, we give the detailed definition of guiding property. We call a vector has m epsilon guiding property if all ones but epsilon getting in some m consistent positions. We do not ask them getting in first m positions. Then we made some experiments on the DFR with both arrow and K satisfying guiding property. We varied the value of m within the range of 4,500 to 5,200 and epsilon 0 or 1. The x-axis represents the parameter m and the y-axis reflects logarithm DFR. Under BAC 128 parameter, we can observe a DFR in this interval. 2 to the power of minus 25 is much higher than 2 to the power of minus 128. Considering weak K with m equals 5,100 and epsilon equals 1, we have DFR Km epsilon is larger than 2 to the power of minus 97, where DFR Km epsilon is a DFR when K has guiding property and the arrow is random. The 2 to the power of minus 22 is the DFR we observed when both K and arrow has guiding property, and 2 to the power of minus 75 is the probability arrows having guiding property. However, the probability secret K having guiding property is still too low to affect the DFR average, so we relax the condition. First of all, we no longer require arrows having guiding property. Secondly, we expand the case using isomorphism. The isomorphism in ring phi I is defined as mapping yx to yx to the power of I. And we observe that HO-H1 and EO-E1 cause a decryption failure if and only if the images of phi I causes a decryption failure. So we can use the isomorphism to expand the size of weak case. And weak case size under isomorphism is defined like this. For example, when I equals 2, a vector with weights gathering in first m positions is mapped to a vector with weights gathering in 0, 2, 4 until 2m within these even positions. The complete weak set is the union of every isomorphism of the original weak key set with gathering property. Note that the I isomorphism maps the weak key set exactly as the R minus I isomorphism. We only consider I ranging from 1 to half of R. However, the size of new weak key set is hard to measure because one vector could match more than one image. We estimate the overlapping count and give detailed proof in the full version of paper. Due to the time limit, I won't explain it in details. With a new weak key set, we can estimate a more accurate lower bound of DFR average, since we will only ask HO satisfying gathering property in the definition. We can also achieve the same effect by allowing H1 satisfying gathering property. That's where the 2 times comes from. The errors are sampled randomly. We have made experiments on epsilon equals 1 and 2,900 lower than m lower than 4,000. The results are listed in the right table. N is the number we decrypt. F is the number of failure cases. The .5 comes from our sampling method. The DFR is in the logarithm form and P is the probability a random K has gathering property. Furthermore, we have DFR average larger than 2 to the power of minus 116, which is much higher than 2 to the power of minus 128. So the CC security claim should be reconsidered. Moreover, the weak key with gathering property could lead to a decryption failure attack. In the next section, I will introduce the decryption failure attack for QCM-DPC. First, let's consider the attack without ciphertext reusing, which means that distinct ciphertexts are employed for each target. Our main principle is that the DFR of weak keys with gathering property is much higher than the average DFR. So if we meet a key with high DFR, it has high probability to be a weak key. The attack model consists of 3 parts. Firstly, construct ciphertext. We can, for target T, we generate the inverse of DFR weak ciphertext. Then secondly, we decrypt those ciphertexts. And if a failure occurs, we jump to 3, or we change the target and return to 1. Thirdly, we try to recover it using ISD with extra information. We will talk about this method later. Well, this model could recover a weak key. It brings another question, the false positive cases. Some cases might experience decryption failure without possessing the gathering property. We have to admit that we cannot recover false positive cases. Fortunately, we can measure or estimate the number of false positive cases through some methods. The detailed discussions are available in the full version of our paper. Now, let me introduce the key recovery algorithm. Here is a syndrome decoding problem with extra information. Given H, S, and other parameters, we know HE equals S and gathering property information. There exists an integer such that with HO, from A to A plus M is half of W minus epsilon. This is the exact definition of gathering property. How do we connect syndrome decoding with extra information with our recovery attack? We enumerate the isomorphism I and try to recover the pre-image of the K, which is phi I inverse HO and phi I inverse H1. For classical syndrome decoding problem HE equals S, ISD algorithms are the most effective ones with the best complexity. These algorithms have a rich history, including Priant, Standumer, MMT, and so on. All ISD algorithms follow some similar steps. We divide them as random permutation, Gauss elimination, column match, and recover. The random permutation trying to split the arrow E into 2 parts, E1, E2, with similar lengths, where weight E1 is W minus P, and weight E2 is P. P is a very small parameter causing E1 to host the majority of ones. The remaining steps are not changed. Now in our modified version with extra information, here is the basic idea. We guess the beginning index of A, gather the M positions of YO in E1 because we know most of ones getting in here. On the other hand, E1 needs most of ones, which matches this. Gather the remaining R minus M positions of YO in E2 because only epsilon ones are located here. The other positions are permuted randomly. So the total complexity contains two parts. One involves calculating inverse of DFR weak multiplied by P weak to get a decryption failure. For the key recovery part, the false positive probability is denoted as P true, and we can calculate P true in this equation. In the right figure, the purple curve is the complexity of identifying decryption failure, and blue one is key recovery step. The green line indicates 128-bit security. With proper parameters, we find that the total complexity could reach 2 to the power of 116, making it an effective attack. Actually, we have a better attack for BAC. As BAC has no multi-target protection, we can generate ciphertexts with guiding property 1 in pre-process step and use them for any target. We generate ciphertext randomly and collect the inverse of DFR M epsilon weak ones. In the following step, every decryption is made in this weak ciphertext. Another modification is that isomorphism is not used in this model. The complexity of this model contains 3 parts. Getting weak ciphertext is included as the inverse of DFR M epsilon multiply QM epsilon, where QM epsilon is the probability a ciphertext is weak. And the final complexity is 2 to the power of 98, having 20 bits advantage compared with the model without ciphertext reusing. The right table is a comparison of 2 models with the best parameter in our experiments. We can see that the model with ciphertext reusing needs pre-processing, but it has lower total complexity. Finally, let's summarize the whole paper. The 2 main contributions of our work are providing an estimate of DFR based on weak case and proposing decryption failure attacks on BAC. For BAC's designer, we suggest a more accurate estimation of DFR to ensure CC security. Additionally, multi-target protection should be added to avoid attack with ciphertext reusing. For future work, there are several areas to explore. Above all, since parts of our complexity are obtained by experiments, there might exist more effective attack with larger M epsilon. To find this, over 2 to the power of 30 decryptions are needed. Secondly, for simplicity, we split the weight of error equally, while BAC only asks the sum of weight. So more effective attack might exist when the weight is imbalanced. Finally, theoretical model between guessing property and bit flipping might be a promising direction. Okay, that's all my presentation today. Thanks for listening. Please don't hesitate to ask any questions you may have.
Are there any questions from the audience? So I have a question. Is QCM-DPC used to build signature schemes too? And in that case, does your analysis have any impact there?
There are some other application of QCM-DPC, and we only analyze BAC. So the similar phenomenon should exist in other application of QCM-DPC. If they use bit flipping to decode
Thank you. Okay, if there is no more question, let's thank the speaker again.